jump straight into them. First presentation is about modeling and optimizing human performance in XR. So I see we have our presenter online already, so go ahead and take it away.
Thank you, Frank. Welcome everyone. This is Chi Sang. I'm an assistant professor at New York University. I do research in VR, AR, and human perception. So in this talk, I'm going to present some of our previous, recent, and ongoing research around XR-based training, especially focusing on human behaviors. The first line of research I'm going to discuss and share is about redirected walking. The other line is muscle-based neural interface. And if time allows, I will also share some of other research that's happening in the lab. And the first one is redirected walking that we're going to discuss. The idea is this. In virtual reality, we want the people to navigate through a much larger virtual space within a very small, compact physical environment because they cannot see the physical space. We don't want them to bump into walls or obstacles if your physical space is smaller. So to enable this, we'll discuss several aspects. First is the human perceptual foundations that can allow for this altered walking between virtual and physical space. The second one is about computational path planning and scene retargeting technologies to have optimized redirection. And later, I will discuss some thoughts in further extending, improving the system for multi-user scenarios for redirected walking. Right. So this is a current way of common control for human navigation in VR, right? So commonly you can see people sitting in a chair, they use joystick, keyboard, mouse to control the locomotion, which is pretty good for entertainment, for instance. But for professional training, such as the astronaut training, right? So it doesn't work that way because the way we perform tasks is highly related to where we actually go, how do we pick up object, where do we pick up the object, and all that. So using a joystick control keyboard mouse cannot indicate the actual performance of the human training environment-based training environment. So yeah, good for entertainment, not for professional training. If we want to have a realistic training experience as if the person is actually in the task, we require natural walking, that they can walk anywhere they should during the task. But for VR, particularly, there is this problem, right? So through a much larger virtual space, they can be infinite, they can be the universe. But the problem is, in reality, our lab space, for instance, in this example from NASA Hybrid Labs, the problem is we always have very limited lab control space to simulate, for example, the microgravity environment. In that sense, there are obstacles, things like that, chairs, tables, or devices. There may be other users that can take over the space that may bump into the person in VR, right? And of course, the available space is much smaller. So redirected walking is actually designed for solving this problem, such that you want to naturally walk local mode in a much larger space in a virtual environment, but you are actually physically in a smaller space, right? So this is the idea, right? So on the left, this is a smaller physical environment that the person is actually in. And there may be obstacles, there may be other users. And in reality, right, during the task, during the training, the person may move anywhere, may move to other locations. This is the trajectory. We don't want the person to first bump into walls, second, obstacles, third, other users. But in the virtual world, we want to have this experience, right? So the person may walk with the same distance so that we don't change their speed. But the trajectory in virtual environment may take a much larger space that can give the user the realistic sensation of motion, right? To enable this experience in training, we leverage some perceptual modeling, perceptual nature of the human's eye, right? So for those of you who are not familiar with vision science and neuroscience, right? So we were leveraging a human perceptual nature called saccade, right? Saccade is just a fast eye movement, as you can see from this video, right? Whenever we change in our intended focused target, our eyeball quickly rotates to somewhere else. And this rotation can be really fast. The rotation can be about 180 degrees per second to more than 1,000 degrees per second. as you can see from this motion, right? Not only human, but also other creatures, almost any creature with eye has this effect. For example, in this spider, it also has a very fast eye movement here, right? And then there's a problem. So this Y circle shows a user's gaze, right? The problem is the eye is moving too fast and the brain is not as fast, right? So for instance, with 1000 degree per second motion, the eye is capturing so many images, but the brain cannot process so many images within such a short period of time. So what the brain chooses to do is to choose to be blinded. So this is a simulation of the image in our brain, right? So we can see whenever this a circle, which is in our gaze, is quickly moving, the brain is mostly blind, that we don't perceive anything almost, right? So this is some psychophysical experiment results, right? So the x-axis here is time. The y-axis here is our sensitivity to colors, right? You can this area in the middle shows the saccadic period, which means the person is doing this fast eye movement. And you can see our sensitivity to color, to content significantly drops. And this kind of saccadic behavior happens 3 to 4 times per second, more frequent than our heartbeat. That means we have short period of being blind 3 to 4 times a second, but we never realize that, right? And how to transform this human nature to the redirected walking target, as we mentioned, is using this technology, right? So here you can see at the bottom, there's a head. We are showing 2 eyes. This is a simulated image that you see through the VR display, right? At each moment, the eye may quickly move because during this period, the brain is blinded, right? Any subtle manipulation of the image may not be noticed, right? So that we can slightly rotate the image in a virtual environment, but the head doesn't change, and your orientation is actually redirected, but you cannot notice the difference. And we conducted a series of psychophysical studies. This speed can be 12.6 degree per second without users telling the subtle manipulation in a virtual imagery. This is how you turn it to alter the human walking path, right? In this example, for example, if I was the VR user, I was about to enter this tavern, right? What's going to happen is originally just walk straight, get into the tavern. And this is a very long distance. It may take very large space and area in the physical environment, right? But here it shows the user's gaze, right? From the left, you can see whenever the gaze quickly moves, we are slightly rotating the image a little bit, but the person wouldn't notice any difference, right? Because now you can see my original target, which is a tavern, is already rotated. My walking trajectory is also changed in that sense, right? And on the orange curve may show your altered walking directory. You can see the orange curve takes much less space than the blue one, right? Because it's curved, it's more compact, taking less areas, although their distance are the same. And now there's a problem, right? We know we can leverage this perceptual behavior, we can change the user's walking trajectory, but the problem is how and where should we redirect the user in the actual physical environment, right? For instance, if I'm left to the wall, if you redirect me this way to the right, I may hit the wall immediately, even worse, right? So there must be a better planning approach to know where is the best direction that we can leverage and redirect the user's walking path, right? This is called the path planning problem. This is an example, right? For example, here, at this moment, the user may want to enter the tavern, and there's a physical chair the person cannot see right in front of me, right? And say this is a virtual space, and this white dot is the actual target that the person wants to go to. And this is a smaller physical space. There's also obstacles, right? If I don't do anything, the person may just want to go to the white target. What's going to happen is the person may hit this chair. This is what's going to happen, right? And we don't want that to happen. This is the problem that redirected walking want to solve. And as we mentioned, we can change the user's walking trajectory without them being noticing that, right? And for instance, if this is the eye-tracked head-mounted display, we're using the SMI, but this can also extend to HTC Vive Pro I with any high-frequency eye tracker. Say if at this moment we detect, okay, this person does a saccade, which means the person's eye quickly moved, which means the person is roughly blinded in this very short period of time. What do we do, right? And where should we redirect the user is the best. Right? And the idea is this, right? So we just want to guess where the user would likely be in a virtual space. We don't know, but we can guess, right? For instance, if the person is looking at the right at this moment, this might be the likelihood of the person's position distribution, right? So very unlikely I may go to very corner of the virtual space in the near future, but more likely we may walk towards where we are looking at, which is a common sense because we are looking at where our target is, right? So you can see there's a denser distribution over here, right? Because there's a highly likelihood that you walk towards where you're looking at. And then we derive an energy function or loss function that whenever a point is outside of the physical space, we give a very high loss. Or when your point is close to the physical target, we give a very high energy punishment. Our idea is to minimize this loss for all those future potential positions that the person may be in the near future. We don't know, right? But this is the likelihood that we can guess. And what we're gonna happen is remember we can redirect the user by 0.12.6 degree to from minus to positive 12.6 degree, right? That's the allowable change. If you rotate beyond that, the person may notice the difference, right? So it's becoming an optimization problem, right? We search in this range, which is how much we can redirect the user. To which direction can we minimize this loss for all those potential samples? We cannot guarantee all of them, but try to minimize the cost, right? And then we may figure out, okay, probably if you redirect the user towards this direction, there's a low likelihood the person may bump into the wall and a low likelihood the person may bump into the chair, right? In this smaller physical space. And because we want to react this, perform this optimization in real time, because saccade is short, it just gives us about 100 milliseconds to perform what we want to do. Right? So we implement the GPU optimization approach such that this search and optimization can be done real quick, right? And what's going to happen next is this orange arrow shows the best direction we can redirect the user. And what's going to happen later is, okay, so the person does saccade, we rotate the virtual space a little bit. Now you can see this white dot, which is my actual target to go to, is changed, right? The person may walk this way. And you can see the person is automatically guided away from these obstacles and also try to be away from the physical boundaries, which is a wall in some cases, right? So this is the idea of redirecting the user. And because we're using the GPU, you can see this computation can happen really fast. We just need 4 or 5 milliseconds to find the best direction that we can redirect the user so that we can respond to the saccade short time window real quick. Right? These are some demo examples, right? So here on the bottom left, the blue curve shows the user's physical path, right? The orange shows the virtual path. And you can see the real room, which is the orange, which is a yellow rectangle, is a smaller space than the blue one, right? And there's also an obstacle here as a red dot. You can see the person is navigating, naturally walking through a much smaller physical space. Meanwhile, the person can be naturally guided away from bumping into this obstacle, right? And although this blue and orange curve, their length is the same. That means we didn't change the user's walking speed. If you walk 1 meter in the physical space, you also walk by 1 meter in the virtual environment. It doesn't change your speed, but it uses this unnoticeable directional rotation so that you don't perceive any difference, but you're guided away to be safe. And we performed like a relatively large-scale user study. We implemented some games so that the user can wear that, can naturally navigate through the scene, right? So statistically, we can say, okay, by using the saccade redirection, we can save 41% of the area that is usage. That means your physical space can be 41% smaller than the virtual environment. Right? And by further improving this method, remember we talked about the path planning strategy. By leveraging that path planning strategy, we can further save the space usage in physical environment by 34% of the area out of this virtual environment. So we implemented this into the real live demo, more like a game-ish. That you can see this a few years ago. This is a very small demo booth, right? So the person is playing a chessboard game. So he's wearing the same VR headset. We track the eye, we redirect the user whenever saccade is detected. And from the screen, you can see this is more like a chess piece game that the person walk to the chess piece and move the chess piece anywhere they want and then place it somewhere else, right? And we were given a very small demo booth physically. This is just a 16 by 16 demo booth size. And this green curve is actually the real-time logged user's physical trajectory. And the red curve is what actually the user walked through in this virtual environment, right? You can see the person first walked to this black chess piece and navigate around the border and place it back, right? So, but you can see the physical space is only 16 feet by 16 feet, which is about 0.5 by 0.5 smaller than the large red virtual environment. And this is a live demo. We demonstrated to a few hundred people, and barely anyone noticed the change. This is about redirecting by perception, right? So in the recent years, we also extended this type of problem, try to solve this problem by new environment design. Say if the designer is already designed a virtual space, we want to map it to the smaller physical environment. If we just scale that, you can see everything will become smaller, right? Which is unnatural. And we have an automated redesign of the virtual space, although it's previously designed, such that your perceived objects and size might be still natural, but the area can actually be smaller, right? This is the scaling, and we automatically update this system. And here are some other examples that you can see from here, right? So yeah, so these are some redesign such that the perceived object size doesn't change, but you actually the size of the actual entire environment is changed. And this raises some new problem for solving this in a multi-user scenario, right? We have some preliminary results. This is a simple solution. We just, at each frame, we just treat the other user as obstacle using exactly the same method, no further changes. This can somehow work, but you have to assume the two people, they walk really slowly because we have to respond to the new obstacle position every time by treating the other user as a static obstacle, right? So the idea is, the problem is this, right? So we cannot know where the other user is, but if there is some way that we can statistically predict others' motion and location, that can help the system to react much better, right? Because we can pre-plan by knowing the future. So there are some statistical ways, right? So the first one is can use game theory, right? This is an example. For instance, in a multi-user scenario, if we want to redirect, it's very hard. We don't know the future because these other users, they may walk in any way they want. It's not possible to control their behaviors. But one thing we can do is to assume the worst case. This kind of method has been used in, for example, self-driving car to avoid collision. That at every frame, you can just assume other users are trying to hit me, right? They are just walking straightly towards me. This is the worst case scenario. If we can avoid that, more likely we can avoid this arbitrary case. So this gives us some cue or some prior assumption that can optimize the trajectory planning. There are some other cases, right? For example, in this case, because this is a training-oriented XR environment, for training, we have a task. For a task, most likely people perform that in a statistically similar way. For instance, maybe at this moment, this person may just walk to the chair, right? Based on this task. We may have some future prior knowledge of where each person might likely to be. Right? There is some machine learning approach. You can treat this as a multi-agent problem by collecting data for a given task, so that we can have a deep neural network to roughly predict the statistical locomotion for other people in the future, so that our past planning can be early, well prepared to solve this problem. These are just some thoughts. And the other line I'd like to quickly share is about muscle-based neural interface that we have been recently working on. Right? It's about sensing muscles and measure the muscles to have a force-aware XR training. So this is an example of XR training, right? So you want to drill some screws, right? What we know is where the person's hand is, but if you notice, we are missing some knowledge. We don't know how hard the person is pushing this device. We don't know how hard the person is pushing these screws, right? So we don't know the force. And after long-term training, we probably don't know the muscular fatigue. Is the person tired from this task? It's hard to know. We can only know the position of the hand, but not information from the force. So we recently have been leveraging this neural sensor called electromyography, EMG, which is placed on your skin, but the sensor can directly sense the electricity signals inside the muscle, so that we can understand how hard you are pushing object, where your hand is, and whether you have fatigue in the muscle as a metric of training efficiency. So basically, this sensor tracks bioelectricity signals like this. We are leveraging some machine learning approach so that we don't need any additional sensor. We can know the pulse of your hand. We can know how hard you are pushing this target in terms of force. And further, based on this knowledge, we can predict the muscular fatigue in a training setting. Right? So how long should the training be? How should this task be designed so that they can minimize the potential training fatigue? And also we can have a measurement of whether the person is pushing object correctly using the correct force, or is it too low, or is it too high, which is impossible to be seen by cameras. Right? So we have some experiments, like demos like this. So the person in physical world may just press on the object. You can see in a virtual object, when you press this physical object harder, the squeezing of the virtual environment object is stronger. If you press it lightly, there's a physically correct reaction from the virtual environment to give us the correct sensation of physics, and also the measurement of what you're actually doing than just seeing that. Okay. So because we still have a few minutes, there are some other research. If you'd like to discuss offline, I'm more than happy to collaborate and discuss offline as well. One side, as Frax discussed a little bit earlier today, is about visual vestibular conflict. Right. So we have some previous work that measures the perceived vection, which is visual vestibular conflict, to minimize the thickness, which is we compute the optical flow in the retina from rotation, from translation, and we have the optimization approach such that it minimizes the visual vestibular conflict, because you can perceive as low as possible motion from the display, and then to minimize your thickness from vection. Right. We recently have done some other research on predicting reaction time. For example, when you see the target, how statistically does it take you to react to this target by moving your eye to that, right? So we developed some machine learning and statistical neurological model that can predict the statistical distribution of the reaction latency by seeing the target. Right. So that summarizes my talk. I'd like to take any questions you have any, or feel free to discuss offline as well.
So I have a couple of questions.
Yes.
You touched on both of these a little bit during your talk. What walking speeds have you been able to do redirected walking? I guess you have to keep at a slow walk, or have you done any faster walking type of scenarios?
Oh, yeah. So that is a relative concept, because, for example, in that demo booth, right, it was a 16 by 16 feet small size. We had to encourage the participant to just walk as if it's a natural walking rather than running, right? Because the thing is, if you run really fast, there's a less chance that you can perform Saccade, so that we can redirect the walking path. But if your physical space actually gets larger, we can allow for faster speed. It's a function of what's allowable space.
Copy. Thank you.
Yeah.
And you answer I had was related to the size of the spaces that you've used for redirected walking in.
Yeah. For that demo example.
Well, the question I had was, what's the smallest physical space that you've been able to successfully implement redirected walking? But like you said, it's all related to speed and the actual activity that you're carrying out.
Yeah. In that paper we actually have the simulation. For example, with a natural frequency of performing saccade, we have the curve. So basically, the rate that you can save the space is more like a polynomial of the absolute physical space allowed. And in our smallest successful experiment, we were using about the 3 meter by 3 meter large space, again, for walking speed rather than running. That can give us about 30% of space saving between the virtual and physical environment. And we have some simulated analysis as well. Yeah, I'd like to share more about the simulation.
Got it. Thank you. Any other questions?
Hi, I just threw one in chat here. How does the room shape play into redirected walking? For example, like if we had like a, an L shape, or maybe even a maze. I might have missed that.
Yeah, exactly. This great question, right? So this is the example. As you can see, the shape is just a formulation difference. Here you can see whenever your the position is outside of physical space, we have a high energy cost here, right? We have some other a simple formulation that you can just model that like a polygon, and everything beyond that polygon has this higher energy. Anything inside this polygon has a lower energy. So it's just a matter of leveraging this energy function to any shape. We did a non-rectangular experiment as well by simulating that as a polygon shape.
Okay, thank you.
Yeah, sure.
All right, we have about a minute left. Anybody have any question?
Okay. For this particular example, we were using Unity, and clearly that requires an eye tracker system. And we were actually trying to make it more like a Unity plugin, right? So that as long as your VR headset has an eye tracker, and you give us the definition of the physical space and the border of your virtual space, where you are, we can know. The input could be just a sketch of the boundaries. We were trying to extend it to more like a plugin shape in Unity, but it doesn't require any specialized environment or anything. But I need a CUDA because we need to run the real-time optimization.
All righty, well, thank you for the excellent presentation.
Thank you.